So I think everyone has encountered GANs, but I'm going to introduce a little overview of what they are, just in a sense also to give people a notation. So here, my GAN is going to be a GAN task with drawing pictures and notes. Okay? So I have a generator, which I'm always going to write as this little artistic student here, and the generator kind of draws some notes. And then along comes the critic, and the critic takes a set of the notes that the students did and compares it with a set of real notes, and then gives feedback to the students. And then this cycle continues and continues until either the student stops improving or the teacher can't tell the real notes from the same notes. Okay? So this is a sort of GAN setting. You have an adversarial setting where the student tries to do a task, in this case generate a set of images, and the teacher takes that set of images, compares it to a reference set, and gives the student feedback to help the student improve. Okay? One distinction I really want to make here is that this task is not the same as classification. So if the teacher were a very good classifier of real from fake notes, then the student could get away with learning to draw one real note really well. Okay? And then the classifier, the teacher would say, oh yeah, that's a real note, and I'm really confident it's a real note. That is actually not the task. I don't want my student to learn to draw one note, because it would then just like take a picture of that note and keep giving it back. I want the student to learn to draw pictures of these set of notes. And when we look at this setting, we notice that we're actually in the setting from yesterday, where I have a set of real objects and a set of fake objects, and I want to check whether they're from the same distribution. And then the teacher should give some feedback if the distributions are different so that the student can improve its own generative mechanism. Okay? So this is the GAN setting. What I'm not going to talk about today at all is the student. Okay, my generator, you can read papers on generators. What they do, they take a source of noise, they push it through a bunch of convolutional filters, and then out comes the picture. Okay? I am completely uninterested in that. All I care about is the critic. And today I'm only going to talk about the critic and nothing else. Okay? So here is the drawing from yesterday. So this is my sort of vocabulary of different divergence measures. I've got my integral probability matrix on the left, I've got my F-divergences on the right. All of these different divergence measures could be critics. They're all measures of difference between probabilities. I can take my set of real images, my set of data images, I can push them through these critics, and then I can use that to train my GAN. Like any of these critic functions could in principle give me the kind of feedback that I need to train my adversarial network. Except for total rotation, which is okay. Okay. So let's first of all think about F-divergences. Okay? So here is the Jensen-Shannon divergence. The original GAN paper was proposing to use the Jensen-Shannon divergence as a critic. On the plot here, I've shown an example of two densities T and Q. Okay? So T is a little triangle density centered in the origin, Q is away from the origin. My task would be to move my little red triangle towards my blue triangle. My Jensen here the support of these densities is disjointed, they don't overlap. So my density standard divergence in this case is log 2, always log 2. You can figure that out with the line log 2. What if I move my right one closer? It's still log 2. So Jensen-Shannon divergence is a little bit of a problem because what it is, which I've sketched here in the corner, it's a bad teacher. It's a teacher that says like whatever the answer you give, unless it's perfect, the teacher just says you're wrong. Okay? So I put my density here, the critic says no, I'm wrong. I put it here, still wrong. Okay? So the angry teacher that I put here is the one I'm going to use when I have a critic which is unhelpful. The critic just yells at you and says no, that's not correct, rather than giving you some feedback about how you can improve. Okay? So Jensen-Shannon apparently is a terrible critic, right? Because how am I going to optimize over a critic when the only feedback that I get is no, you're wrong, you're wrong, you're wrong. Okay, that's not very helpful. So obviously GANs work in practice. So what do people actually do? Well, they do a couple of things. So one is that they don't actually compute and transform the Jensen-Shannon or put approximation to the Jensen-Shannon. They approximate the Jensen-Shannon in a reasonably loose way. Okay? And then they also alternate improving the approximation of the Jensen-Shannon with improving your generator. Okay? So it's not that you start off with a really good approximation to Jensen-Shannon, you start off with a pretty poor approximation, and then you improve it while improving your generator. Okay? So this is something that I'm going to return to. I'm just sort of hinting at this point that it's not necessarily Jensen-Shannon that is being used as the thing most of the time. And so that's probably one of the reasons why I have to look at this. But I'm going to come back to this point in much more detail. The other thing that you could do is to add a little bit of noise. Okay? So let's look at this picture again. They're not overlapping. But if I added a bit of Gaussian noise to my cube, then they would be overlapping, and then I would get useful feedback. But one has to be careful, because if you add just a tiny bit of noise, the amount of feedback you'll get will also be very small. So it's not that you'll get exactly the same number per here, but you'll get numbers that are extremely close. So that's better than nothing, but it's a very poor signal, even so. If you add too much noise, then you've distorted your blue sample so much that maybe you're not going to get a very good approximation of it from the student. So you can't add too much noise, you can't add too little noise, you have to add just the right amount. Is that clear? Yeah? One of the interesting things that was proved more recently is that adding noise is equivalent mathematically after some approximation to doing a data-dependent gradient regularizer. So this is actually very interesting. This is another thing that we come back to. It's not that you're getting KL, it's that you're getting an approximation to KL that depends on the problem that you're trying to solve. This is another point I'll come back to. It's I'm giving you lots of previews here of what a GAN might be doing. Yep. So your question is where do you add the noise? So all that we want is that the support of my red and my blue have some overlap. I could achieve that by adding noise just to the blue, or just to the red, or to both. If I add a little bit of noise, the amount of signal that I'm going to get for my generator will be small, because the amount of overlap will be very, very tiny. If I add too much noise, then I will distort either the generator samples or my real samples or both so severely that I won't get a very good generator, because the samples that I get will look nothing like those samples because I've added so much noise to them. Yep. Right, exactly. Precisely. So if I was doing images, I would add noise to my images. Now, that means blurry images, right? You don't want super blurry images because then you're getting a terrible generator. Yep. Yep. Right. So, I mean, your question is could you make sort of a noise distribution that wasn't isotropic, that was sort of aiming towards your data? Probably, but then you'd need to know a lot about your problem, right? And so if you knew that much about your problem, then, you know. So I'm just using a quite naive approach, which is the approach that's used in practice here. Yeah. All right, so F-divergence on its own, it's a terrible critic. It just yells no at you, everything you do. What about Wasserstein distance? Okay, so Marco has taught about this. I'm just giving here up a little reminder of the dual form for the Wasserstein distance. I'm finding a function with a Lipschitz norm less than 1, which maximizes the discrepancy in expectation under P and Q. Okay, and I've done a little plot here, which is the solution of this Wasserstein distance for the same data set as before. So you can see that the slope here is bounded by 1 for this line. Now here are my little sketches that I've got a helpful critic. My critic is actually going to tell me when I'm getting closer. So I'm moving my points closer. You'll notice the W1, the Wasserstein distance, goes down. It goes from 0.88 down to 0.65. So this is a helpful critic. This critic, as I get closer, it's telling me, yeah, you're on the right track. You're getting better, okay? So Wasserstein is a helpful critic. And indeed, Wasserstein GANs are one of the most interesting GANs. Although what a Wasserstein GAN is actually doing is something we're going to get back to later in the lecture. Okay, what about MMD? So MMD, which we encountered yesterday, I'm looking for a function in a unit ball in a reproducing kernel Hilbert space, which again maximizes discrepancy between expectations under P and Q. MMD is a helpful critic. Here MMD is 1.8. I've moved my points closer, it drops to 1.1. So it's telling me that I'm improving. So it seems I have a helpful critic. Or do I? So what if I use a very narrow kernel? So here MMD is 0.64, and here it's still 0.64. I mean, it's dropped a tiny, tiny, tiny amount, but not very much. So here MMD is an unhelpful critic. It's just yelling no at you every time. So whether MMD is helpful or not, in fact, it's a little bit more subtle. It depends on if I've chosen a good kernel bandwidth. Okay? So here I've chosen too narrow a kernel. My MMD is an unhelpful critic. Here I've chosen a kernel which is broad enough. So here my MMD is a helpful critic. It's telling me when I'm getting closer. So MMD may or may not be a helpful critic, depending on whether I've chosen my bandwidth well or poorly for my problem. Okay, so using MMD for training GANs is actually a very old idea. It was done in ICML in 2015 and also in UAI, same year. Like 2 papers came out with that idea pretty much at the same time. There is an issue though. And the issue is even on top of the issue of choosing the right width for my kernel. So here are some handwritten digits which are generated with an MMD GAN. And you'll notice they're not actually very good. They're very grainy. The reason is that MMD, with just a generic smooth kernel, has sort of no idea of what features of images matter. And so, you know, it just has a set of pixels and it needs to sort of generate these pixels with the right probability, but it has no sense of sort of local spatial structure. So I need features that actually are image specific. As soon as I say like I need image specific features, you should immediately think convolutional neural nets because they are the state of the art for that, okay? So here is what we actually do. Our critic is a hybrid. Our critic takes the images, pushes them through some convolutional neural nets, and then computes the MMD on top of these features, okay? So first I take my images, I transform them through a CNN, I get some output features, and then I compute my MMD on those output features. So that means that I'm computing my MMD on extracted features from images that are much more informative than computing it on the raw images. And you know, as I've shown with the intensity of the number of citations here, this idea has been used like a tremendous amount. On this side here, we have Wasserstein GAN and WGAN-GP, which use a linear kernel on the features. In these examples here, we use maybe a Gaussian RBF kernel, maybe something called a Coulomb kernel on the convolutional features. So these are the approaches we need to take if we want a good critic for images. So now the challenge becomes, well, I've got these convolutional neural net features, I need to train them. How do I train them? So this is itself a little bit of a challenge. So
to show you how I'm going to train these, I'm going to remind you just a little bit of what we discussed yesterday. So remember, I said yesterday the most interesting way of thinking about MMD for the purposes of understanding how GANs work is in this integral probability metric form. Okay? So how do I compute my integral probability metric between samples from P and Q? Remember how I did it yesterday. I took these little, I put little Gaussian bumps, my kernel bumps on my blue points. I put little red, little red bumps on my red points. I subtract the red function from the blue function, and then my witness function is the output. Okay? So I add up all the blue bumps, I add up all the red bumps, I subtract red from blue, that's my witness. And you can see that it's positive on the blue points and it's negative on the red points. Yep. Right, so remember, like, my MMD is like expectation under P of F minus expectation under Q of F, right? So here F is negative, but then I subtract that, so it's positive, and so I get a positive number, right? It's, EP of F minus EQ of F, but F is negative where there are more Q samples, so minus minus is plus, and so I get back my positive number, yep. So this is the witness function, and this is, I think, the most important and useful way of understanding how MMD is like witnessing its samples and telling the difference. So what happens now if, rather than computing MMD directly on my data, I compute it on nonlinear features of my data, which is what I'm doing now, right? Because I've put in these CNN feature banks. So let's look at this in the simple 1D example. Here, I have chosen a nonlinearity, and I've computed my kernel on the nonlinear function of my data. Look how much the witness function has changed. It's gone completely crazy, right? And you can even see what's going on. So in this part of the space here, like to the right of the plot, you can see the kernel is very narrow. But actually, as I move in this direction, the kernel gets broader. There are other things that can happen as well. So the kernel needn't be symmetric anymore. Right? I don't have a translation invariant kernel anymore. It might be wider on one side than the other side. So there's all sorts of distortions that I can have in my space, which will depend on where I am in my space when I compute my kernel on nonlinear features of my data. It's still positive definite, it's still a valid dot product. But what I've done is I've distorted my function a lot. So this is the sort of image you should have in mind when you're thinking of what the witness might look like when I compute it on nonlinear features of the data. I'm distorting my witness function around quite a bit, but in a hopefully informative way, hopefully in a way that allows me to pull my red points towards my blue. Yep. Right, so the kernel itself that sits on this nonlinearity, always the same, exactly right. So the nonlinearity is entirely responsible for making it narrower, broader, asymmetric, and so on. No, the reason why not, so that would be an approach, but look at this red kernel here. It's not just that I've made it wider, I've also changed the shape. And that's actually important, like it's more than just choosing a different width for different parts of the space. I actually want to distort the kernel. Particularly in image space, like images occupy a very low dimensional submanifold in a high dimensional space. So I might want my kernel to be very anisotropic. I don't want it to fill the space, I want it to just follow this manifold structure. Yeah, so exactly, like my kernel should be something which is sort of spatially dependent and not translation invariant and not isotropic. Yep. Any other questions? Yep. Right, so absolutely we must learn the parameters of the CNN. So remember with a GAN, I have updates to my student and updates to my teacher. My updates to my teacher are learning these nonlinearities, are learning in this convolutional neural net or whatever nonlinearity that I choose. But this is learned, this has to be learned. Yeah? That's right. If I wasn't doing images, I would use different neural nets. Yeah, I would, if I was doing text, I would use a text specific, some, yeah. But you know, GANs, like the sort of killer app for GANs is image generation, right? And so like that's why if we can't do that, then we would already be worried. Yeah. Okay, so this is the distortions that happens. So now I'm going to introduce a toy problem, and this toy problem is going to illustrate a bit how difficult it is to train features for critics when we're using these neural nets. Okay, so you know, I need, when I learn my features, my convolutional neural net features or whatever neural net features, I want to get a useful, helpful critic out, right? I want my critic to tell me how to improve. I don't want it to just yell no at me every time I do anything. Okay? Now, what you might think is, yesterday we talked about MMD, and we talked about maximizing test power. We said, okay, like what's the best kernel? The best kernel is one that maximizes the power of a statistical test. Okay? So it seems that that might be a good way to approach this problem. Because, you know, if I maximize the power of my statistical test, I know that my critic is very reliable in distinguishing my real from fake samples. So that seems like it's a good critic. So let's do a poll. So who thinks that maximizing test power is the best approach for critic design? So who thinks it might be a problem? Good. That is the right answer. So here is the example, right? This is a fantastic critic. This has amazing test power, because it can distinguish red from blue very reliably. But it's a terrible critic for training because it's too good, because all it does is yell no at you every time. And you know, it's right, because you know, the red sample and the blue sample are from different distributions. So from statistical testing viewpoint, it's a great critic. From a training viewpoint, it's a terrible critic. So, yep. That's right, that's right. So if I maximize my test power, you know, that gives a terrific hypothesis test. It gives a terrible critic if I want to use it to train again, because all it's doing is saying, like, I'm very confident these are from different distributions, which is true, but not useful, because my poor student is just being told that they're wrong every time. Yep. So that's exactly what the purpose of this training is, right? I want to just, like, I want to descend on the witness function. I mean, I want to descend on the gradient of my critic to move my red to my blue. But, like, look, you know, in this case, what's happened, I'm moving my red to my blue, but my MMD has gone down a tiny, tiny amount, like such a small amount that the gradient that I would have would be infinitesimal. It would be so small that, you know, I would never, ever get my red to my blue in the time that I have to run my code. Okay, so here is a toy example, and I like this toy example. I'm going to return to it a few times, okay? So in this case, the target is this blue half moon, right? These are my real samples. And my generator is starting off by generating red samples. So it's generating samples sort of uniformly in a square. And I would like to pull those red samples. I would like to give a signal to my generator to pull those red samples inwards towards this moon shape. Okay? So this is sort of a very simple GAN setting, which is in 2D, so that I can actually visualize what's going on. Now, because it's in 2D, like classic MMD isn't too bad with this, okay? So here is the witness gradient, which is what I want to follow, like to improve my model, for the classic MMD with a standard Gaussian kernel. And you can see that actually, you know, this witness gradient isn't too bad. It's pulling my red points towards my blue points. It's sort of missing parts of the space though, so it's not giving a very good signal in these corners of my square or in this part of my space, okay? So it's not that it's giving a signal to my generator over all of the space, but at least it's telling my generator some of the points that it needs to move and where to move them to. So, you know, it's not a disaster. And in practice, you know, in 2D, this is too easy a problem, so it's going to solve it. This illustration here is to show you what the kernel looks like, okay? So I'm evaluating the kernel function at different points in my 2D space. These evaluations basically are uniform across the space, right? Because my kernel is just a standard Gaussian kernel. Everywhere I put the kernel, like if I put it here, I put it here, I put it here, I get the same shape. The little circles I'm doing are isolines. So these are sort of like, you know, quantiles of my kernel. And it's showing sort of a particular contour line of my kernel in different parts of the space. because I'm using a Gaussian kernel, these contour lines are always the same shape. They're always circles. So is this plot clear? This is a very important plot, so it's important that you understand that. Are there any questions about that? Okay, so these are the shapes of my kernel, and these are the gradient lines these are the gradient arrows and amplitudes of my witness function. So I compute my witness function by, putting the kernel on my blue points, subtracting the kernel on my red points. Then I compute the gradient of that witness, that gives me my arrows, and that tells me how to move my red points so that they approach my blue points. Is that all clear? Yep? All right, so now let's compute the witness on features of my data that I'm going to train. In this case, I'm using, actually, rather than a CNN, I'm in 2D. There's no point in using a CNN. I'm using a fully connected network with ReLU nonlinearities. It's 4-layer, and there's a skip-through connection from layer 1 to layer 4. Okay? Now, these are the gradients of the witness for this trained set of features. What do we notice? Let's compare. Okay, here are the gradient lines for the MMD with untrained Gaussian kernels. Here are the gradient lines for the trained ones. So it's a lot sharper, and it's a lot more focused around the target. This is not a helpful critic. This is a critic that says that unless I'm really, really close to my moon, I'm just going to be told nothing. I'm not going to be told where to go. I've learned these CNNs, I've learned these ReLUs, this 4-layer fully connected net, just by maximizing my MMD. I've said, maximize, in a sense, like the value of the MMD that I get. But when I do that, I get a very unhelpful critic. I get a critic which is very confident that blue and red are different, but it's not telling me how to move my red points so they approach my blue points. Now let's look at what's happened to my kernels when I evaluate these kernels on this 4-layer network on my data. These are what my kernels look like. So that's pretty crazy. Like, they're very, very narrow. They do follow a little bit the contour of my blue rather. So see this red kernel here? This is the isoline of my kernel, at some point in space. And it's very, very narrow. So this is sort of like when I'm maximizing my MMD over my features, it's like I'm overfitting massively to my target. Which is great if I want to distinguish my target from my source, but not so good if I want to train. So, compare these kernel shapes to the kernel shapes here, right? You can see by maximizing my MMD just how badly I've distorted my witness function. So this is not a helpful witness function. Is that clear, or are there questions about this? Yep. So do I assume the same network? Yes, yeah, this is important. So the bandwidth of these kernels is exactly the same as the bandwidth of these kernels, but here I'm evaluating kernels on a 4-layer fully connected net on my data, which I've trained. I've trained it to maximize MMD. And it's really great for telling red from blue. If I was doing a statistical test, I'd be super happy with this. But it's not so good for training because, these poor red points over here, like, no one's telling them where to go. Okay, so this is a problem, right? I've got my critic. I've said, well, train my critic by maximizing it over the set of convolutional neural net features, or in this case, fully connected net features. And then I've got a very unhelpful critic out. And if you run your GAN with this critic, it's just going to get stuck. It's not going to improve. It's not going to do anything. So that's unfortunate. So what we need is some way to regularize, right? When I'm maximizing my MMD, I shouldn't just maximize it. I should maximize a regularized version of it over my critic features. So what's a sensible way to regularize? So, okay, yeah, I should put this. This is my angry critic. So this is what I've managed to achieve so far. Okay, so what we published in Europe's last year is a way to regularize our witness function when we're learning convolutional neural net features or fully connected neural net features or whatever your favorite neural net features are on the data. And this is what I'm going to describe next. I'm going to describe a regularization strategy so that I don't get out my angry critic, but I get out a helpful critic. Okay, so this is the regularization approach that we use. Okay, here is the sort of perturbed maximum mean discrepancy, which I'm going to be optimizing. Like, this is my critic function. But what you're going to see is that I've got a slightly different constraint here. Okay, this fs less than or equal to 1. This is what I've used to replace my earlier MMD constraint. What is this fs norm? Okay, it's a combination of 3 norms. It's the original norm, the original RKHS smoothness norm, plus a couple more norms. This middle term here, which I've done in red, this is the important one. Okay, so what this one does is it says that the gradient of my critic, evaluated over the support of my real points, should be pretty flat. This is a data-dependent regularizer. Okay, I've also got a variance term in here, which I need, but you know, this term here is, I think, the important one to think about. So let's go back a couple of slides and see what that means in respect of our data set. What that means is that as I move around my set of blue points here, my critic function shouldn't change much, right? The gradient of my critic should be flat as I move myself around my set of real points. And I think this is a useful thing to do, right? Because it's saying that, like, my critic function shouldn't be changing a lot if I'm in the target distribution, if my data is generated according to my target. Okay? It should only have a steep slope when I move away from my target into this region here. But once I'm in my target, it shouldn't have a steep slope. So it's a data-dependent regularizer for my critic. Are there questions about that? Okay, so let's use this data-dependent regularizer. Okay, so an issue is, this is a beautiful idea. Unfortunately, it's not computationally feasible. So what we do is we approximate it. And we approximate it by this thing I'm going to call SMMD, scaled MMD, where the MMD is scaled by this quantity here. And this quantity here is sort of like a combination of the gradient and the derivative norm of my critic features, okay? So I'm sort of saying, like, rather than my critic function not changing much as I move around my target, I want my critic features not to change much as I move around my target. And this is something I can compute and enforce, which is not the case if I'm just trying to solve this. And what you can show is that actually, you know, this SMMD is an upper bound on the target. Okay? But you know, the crucial point is this. I want my witness function not to change much as I move around in the support of my real points. And you know, this is a sort of data adaptive regularizer. It's a way of enforcing smoothness in a way that makes sense for the problem that we're actually attacking. Okay? So let's look at what this does in our simple problem. So here is my source points, here is my target points. And I have, again, like my nonlinear features are a 4-layer fully connected neural net, etc. Okay? So here is the gradient of my witness using this regularizer. There's a little point at the bottom here which I want to emphasize. This is in the early stages of the critic optimization. So that means that I haven't run SGD to convergence for my critic, I've just run a couple of steps. And what you can see here is that this is a more helpful critic. It's giving me a gradient signal a little bit further from my target. So it's moving my points inwards towards my moon, but it's not sort of focusing very narrowly on the moon structure. Okay? And this is what my kernels look like. So you can see that these kernels are doing what it is that I told them to do, right? Remember that I said that my critic witness shouldn't change much as I move around the moon. That means that my kernels basically will follow this moon shape. So my kernels will sort of like take the shape of my target distribution because, you know, a kernel is a measure of similarity. My kernel shouldn't change as I move around my target. That's what I've enforced with my regularizer. And so the functions that I'm getting out are these sort of nice functions which tell me how to climb. Now let's run a couple more iterations. So now at the bottom, I've written late stage of the critic optimization. So I've run additional iterations of this optimization. And you can see now that the gradient lines are sort of focusing in on the moon. So in the early stages, I'm sort of dragging my points from around my space towards the target. In the late stages, I'm assuming I'm close to my target and I'm pulling my points even further in. So, you know, at the start of the optimization, this would be a terrible critic because only it would only give a signal to my generator when it was near the target. In the early stages of optimization, this is a great critic because it's telling me where to move my points to approach my target. Of course, in the late stages, it's not such a good critic because it's too diffuse. Okay, so there's actually two things that are going on here. One is that, like, I have a problem-specific regularizer, which is telling me my function should be smooth over my target. And I also have, the fact that I'm alternating optimizing my generator and my critic, which means that in the early stages of critic optimization, I have a very weak critic, I have a very diffuse critic, which is giving me a gradient signal for my whole space. In the late stages of optimization, it focuses in on the target. Are there questions about that? Yep. That is right. So this isn't perfect, right? So, ideally I would have a gradient field over my whole space that would put all my points to my target. I'm not getting that. This is why it's like, there's work to be done. This is not the final answer by any stretch. But it's better than just optimizing MMD over the features. Like, I'm improving that. I think there is much, there's a lot of room to make even more sophisticated regularizers for these problems. So this is just this, this is just the start of the journey. Yeah. Any questions? Okay. Yeah, these are what the kernels look like in the late stages. So you can see that in the late stages of the optimization, the kernels are like conforming even more to the target distribution. I mean, they're not massively overfitted like we saw when we just maximized MMD without a regularizer, but they're still a little bit more concentrated around the target, which is what you want in the late stages of the optimization. Okay, so these are empirical observations. Like, as I said at the start, I cannot prove that GANs work. So what I'm telling you right now, and this is sort of stuff we've even thought about in very recent months, so this wasn't even in the original NeurIPS paper. These are sort of my conjectures about why it is that GANs are working. So, to prove this and to actually make this formal, like, this is, I think, a project that I hope that everyone is going to take up, because I think it will be really useful to figure out what on earth GANs are doing. But these are our observations that we've made empirically. Okay, so the one is that we benefit from using a data-dependent witness class. We benefit from using a data-dependent critic. So what that means is, like, when I compute MMD in, like, the lecture yesterday, my function class didn't care what problem I was trying to solve. It was a generic off-the-shelf function class which I would use, for any problem. I'm just saying f should be smooth. In this case, I have a problem-specific function class, right? The smoothness constraint depends on my P. If I have a different problem, I have a different notion of smoothness. And for GANs, this is essential. I don't think you can use a generic off-the-shelf critic for GANs. The reason is, in GANs, your generator has limited power. You want it to focus on the features of the problem that you're trying to solve, right? If I use a generic off-the-shelf critic like KL, like Wasserstein, like MMD, it doesn't care what features are useful for images or not. It just says, like, move the probability mass from where it was to the target. If I use a problem-specific regularizer, I can focus in on features that are useful for my problem. Because my generator is limited, I have to do that. Okay, so problem-specific witness classes or problem-specific divergence measures are essential for GANs, I would say. Okay. By the way, you might think, well, okay, what you've just talked about is GANs based on integral probability metrics. What about F-GANs? Aren't they just minimizing KL? Aren't they minimizing Jensen-Shannon or chi-squared or whatever? Okay. Look closely at these papers. The more modern ones actually don't compute like the KL. They compute an approximation to the KL with a data-dependent gradient regularizer. So again, they're not using the KL. They're using a problem-specific approximation to the KL. And the function class they're using depends on their problem, just like for the IPMs. So to get a successful GAN, you cannot use a generic off-the-shelf divergence. You need to use a problem-specific divergence. And that's what works. Yep?
So imagine we have two GANs.
That's an excellent question. So the question is like, benchmarking GANs, like how, what is the measure to say that one is doing better than another? This is something I'm going to talk about shortly. That is also absolutely not a solved problem. Like all of the methods that are out there now have problems, effectively. But there are, some which have very obvious flaws, others that still have less obvious flaws, but this problem hasn't been solved. So at the moment, the way that you benchmark a GAN is by like looking at the pictures and seeing if they're pretty. It's a bit sad. Okay, yeah. Right, so this is absolutely the case. So, the function that you get depends on the optimization path. And, you basically like, you run a few iterations of the optimization for your critic, then for the generator, then for critic generator. So this is why I say very clearly, I don't know how GANs work. Okay, so indeed the function class that you get depends on your optimization path. And it so happens that it seems that the function is more diffuse in the early stages and more concentrated around the target in the later stages. I can't prove that. Everything that I'm saying is purely empirical observations. Are there any other questions? Okay, so, oops, I don't want to go there yet. Data-dependent regularization matters. You shouldn't use a generic off-the-shelf divergence. You should have a divergence specific to your problem. That's what people do in practice, and that's what works. Okay, next thing is, relating to the question I just got, if at the very start of my optimization, I train my critic to convergence, it's an unhelpful critic. It just yells no every time. So it appears that what you need to do, on top of using a problem-specific divergence, is not to train your critic too much in the early stages so that it sort of covers your generator space and gives you a useful gradient signal. So, these two things appear to be what makes GANs work. Problem-specific divergence and alternating your training of your critic and your generator so that in the early stages your critic is a weak critic. It's a critic that doesn't just yell no, it gives you a gradient signal for your whole space. It's smoother than it would be if you wanted just something which is very accurate at distinguishing real from fake samples. So, the sort of research program now is to actually prove that these two bullet points are more than just a conjecture, that they're actually what GANs are doing. And that's, an open question for you guys. Like, I'm hoping to see some papers at some point which succeed. Okay, so the other one that I want to return to now, like I mentioned a little bit earlier, WGAN and WGAN-GP. Okay, and these are other GANs that use integral probability metrics. So computing the Wasserstein distance exactly is very tough, right? Particularly in high dimensions, and images are in high dimensions. So, you can use a sinkhorn approximation. This is not what these papers do. The paper that I'm going to describe is going to be the next one down, not Wasserstein GAN, but WGAN-GP, which works a bit better in practice. What it does is shown on this cartoon here. It makes the gradient close to 1 at points somewhere between my real and fake points. So I take a real point, I take a fake point, I draw a line between them. Somewhere on that line, I make my witness gradient close to 1. Okay? So, I'll show you now in mathematics what that means. I've got my generator. It's generating samples from a noise source. So Y is generator applied to a Gaussian noise. I've got my critic. My critic is just a witness, which is a linear function of my convolutional features. So it's like I'm using an MMD with a linear kernel. Okay? So I use my MMD with a linear kernel. This is what I optimize. Expectation under P of F minus expectation under generator of F, plus this original term. What is this term here? It's just the gradient of my critic somewhere between a real and fake point. So what is WGAN-GP really doing? It's doing a problem-dependent gradient regularizer, just like the MMD did. And, I would argue that's why it works. So unfortunately, Matus isn't here right now, I guess. So he told me actually yesterday that he took the WGAN-GP regularizer and then iterated, like solved it a bit further using a much better estimate of the Wasserstein distance. And the samples got worse. So I think that's interesting because what that tells you is that actually, you know, to the extent that WGAN-GP is working, it's working because it's not using a Wasserstein distance. It's using because it's using a data-dependent function class. And the moment you start using a generic Wasserstein distance, you're going to get a worse solution. So, yep. Right, so if I was, the issue is, sorry, so these plots here, if I did the Wasserstein GP regularizer, these plots would look very similar, indeed. Okay, bearing in mind though, like, to get these isoline plots, the gradient plots would look similar. We wouldn't get these plots because we have a linear kernel, right? So it's not, but these plots would look very similar, yeah. So the gradient signal you would get would have this same sort of behavior, which is, you know, good, yeah. Are there any other questions? Okay. So that's what WGAN-GP is doing. So yeah, it's a data-dependent gradient regularizer on your witness class. And I would argue that's why it works. The data dependency is key. Okay, so you might also wonder about, you know, I've talked about WGAN-GP, which is using a linear kernel. I've talked about using nonlinear kernels on my convolutional features. Is there any difference? Like, is it, does it help or does it make it worse to use a linear versus a nonlinear kernel on your features? So here's an example where I've used exactly the WGAN-GP regularizer for both of these GANs. Okay, like I've said that the gradient should be close to 1, somewhere between a real and a fake point. On the left, I've used a nonlinear kernel. On the right, I've used a linear kernel. The scores I've got here are called KID. This is a score of quality for GANs, which I'm going to introduce a little bit more later. All you need to know for the purposes of this plot is that, oops, you know, actually, these are actually pretty much the same. So it seems from this plot that we don't really get much of a difference in our performance if we use a linear kernel or a nonlinear kernel. So this is using as our Critic features, the DC GAN one. So the Critic has like F2, F4, F, and 8 left convolutional features in layers 1 through 4. In these plots, F is 64. So these are reasonably powerful Critic features. So as far as this goes, it seems there's not a difference. But let's now use a less powerful Critic. Let's reduce F. Let's shrink the size of our filters for the DC GAN Critic and see what happens. Okay, this is what we get with shrunk filters. So look down here at the bottom of the plot, there's F. I've made F 16 now. These are much simpler Critic features. On the left, I've got the plot with the nonlinear kernel. On the right, I've got the plot with the linear kernel. And notice in this case, you get some really ugly things. Like look at this bottom one here. It's very blurry. So in this case, basically, like the kernel features have taken up some of the slack. So I've simplified my Critic, but because I've also got these nonlinear kernel features, I'm still able to train my GAN and get good images out. If I use just a dot product between the convolutional features, so a linear kernel, my GAN basically converges to images that are not very nice. So basically, when I'm using my kernel on my nonlinear features of my data, I'm getting a bunch of features for free because my kernel has those features built in. If I use a dot product between the convolutional outputs, then I don't have those free features and my performance gets weaker. Another thing that we noticed as well is that, and I don't have these plots unfortunately on this slide deck, when we're training, we tend to train faster, we converge faster using the kernels on the nonlinear features versus using just the features on their own. And the reason is because, like, you know, because I'm using my kernel on my features, my Critic is in a sense a more complete Critic than I would use if I was using just a dot product between these features. So it's giving a better signal to my generator. Okay. So now I'm going to get back to the question that I was asked earlier of like, how do you evaluate GAN performance, right? I've got my fancy new GAN. I want to compare it to like other stuff. I want to do it hopefully not by just like squinting at pictures of bedrooms and thinking that one bedroom is nicer than another bedroom. I want something a little bit more formal. So I emphasize here again, like, this is not the final word. I think there's a lot of work to be done to improve benchmarking GANs, but this is currently some reasonable ideas. Okay, one of the most famous GAN evaluation scores is the inception score. So this is the inception score, expectation of the exponential of KL py given x on py. What does this enforce? Okay, so let's say that I've got a GAN and it's generating, objects. I've trained it on CFAR, it's generating like, houses, cars, horses, whatever. What I want is that these images, when I classify them, the predictive label distribution should be very sharp. Okay, so if I take my output of my GAN and I put it in a inception network classifier, I should be very confident of the label. If my GAN is generating a horse, my inception should be very sure that it's a horse. The other thing is that I should generate, a good selection of items. So if I'm training on like, cars and cats and dogs, I want to get actual, all three of these things. I don't want only to get cars out. Okay, so the two things that I want to enforce are that I need to be confident about the label of my pictures, and I need to generate pictures from all the image classes. That is what inception satisfies. So inception actually, like, it's a good idea. One limitation though is like, imagine that you've trained your GAN on celebrity faces. Well then a classifier is kind of like a meaningless thing, right? Because there's only one class and it's face. So, or if I'm training on bedrooms, there's only one class and it's bedroom. So unless I have a problem on which I can apply a classifier, inception network isn't very useful. So, this is inception. It's great for CFA, for example, where I have a good classifier, but it's not so useful for other domains where I don't, or where there's only one class. Okay. So another one was proposed. It's this thing called Frechet inception distance. So it's basically the Wasserstein 2 distance between Gaussians fit to the pool 3 layer of the inception network. So rather than using the inception network as a classifier, I look at the pool 3 layer, I fit a Gaussian to my real samples, I fit a Gaussian to my fake samples, and then I compute the W2 distance between real and fake. And I have that in closed form. So at least this doesn't rely on a classifier. It relies on inception features. Are they good, are they bad? We don't know, but at least, they're reasonable image features. And I fit a Gaussian to some number of those features. So what might be the problem with FID? This is actually a rather subtle problem. Here is the FID computed between, I think this is CFAR, yeah. So I just take my CFAR set, I split it in two, I compute the FID between the first half and the second half. So in principle, these are perfect images. Like this would be what I would get if my GAN was so good it would generate absolutely like flawless CFAR images. But my FID is not 0. It's actually pretty high. And the FID that I get actually depends on how many samples I feed it. So if I feed in 2,000 samples, I get one number. I feed in 4,000, I get another number. I feed in 6,000. So how good my generator is depends on how many samples I've seen. That seems a little bit off, right? The reason I get this behavior is that FID, the empirical estimate of FID, has a very severe bias. That means that the expectation of my empirical estimate is not equal to the population estimate. It's actually much bigger than that population estimate. And that means that when I compute the FID, between two subsets of real samples, which, where it should be 0, I'm not going to get 0 out. I'm going to get a big number. So, FID has this issue. What you might argue is, well, okay, it has this issue, but as long as we compare our generators using like a particular number of samples, like 5,000, maybe the ordering is preserved, right? So, if let's say GAN1 is better than GAN2, if I evaluate both GAN1 and GAN2 at 5,000 samples, then I should always find that GAN1 is better than GAN2, even though the actual value of the FID depends on how many samples I've seen. So if we all agree on the number of samples to use, then we should always get the same ordering for our GANs. So the bad news is that this idea doesn't work out. The ordering of the GANs also depends on how many samples you've seen. So I'm going to skip this example and give you this example here, okay? So here I've generated like two sort of simulated examples of activity at my pull 3 layer of inception. They're a little bit cruder than that. So P1, which is like the output of my feature extractor for GAN1, is ReLU applied to a standard normal. P2 is ReLU applied to this funny normal with a slightly distorted covariance. And Q are the features of my target. So what I've done is I've just taken Gaussians, I've pushed them through ReLUs to give the sort of statistics that I would expect to see in the pull 3 layer of my inception network. And now I'm going to compute FID. All right? So for a particular random drawer of C, so which is my the thing I use to construct my covariance for P2, I've drawn C in such a way that P1 is worse than P2, right? So if I had infinity samples, P1 would be the worst option. Bad news is, if I see 50,000 samples, P1 wins, okay? I got the wrong order. When I see 100,000 samples, P2 wins. So the ordering of my two models, P1 and P2, will depend on how many samples I've seen. So the bias is a pathological bias. It doesn't just depend, it doesn't preserve the ordering of my algorithms. It can flip the ordering of my algorithms as I see more samples. So FID is a little bit troublesome. And the trouble with FID arises because of the bias. Are there questions about that? Yep. That's right. Right, so that is indeed a problem. So like I'm using inception features. Inception features are a completely arbitrary choice. There's no prior reason why they should be good. They're reasonable image features, but you know, this really isn't like the solution to the problem, it's just a solution. The question is, like, given these features, you know, what should be my metric of difference between my two GANs? And I would argue that, like, for any given set of features, let's say I'm throwing away inception, I use some other feature dictionary. If I compute this metric here, FID, on whatever features I like, it will still have this bias problem. The bias problem is not because of the features I've chosen, it's because of the cost that I'm computing on those features. So I've got my favorite feature dictionary. I compute FID on those features for model 1 and model 2. The ordering that I get, whether 2 is better than 1 or 1 is better than 2, can depend on how many samples that I've seen. If I see 10,000 samples, model 1 will be best. 20,000, model 2 will be best. And this will be true whatever features I use. It's a property actually of this expression here, of this equation here, when I'm computing it using a finite number of samples. Does that answer a bit the question, or? Okay. Any other questions? So the issue is, if I repeat the experiment with the same number of samples, probably I'll get the same ordering. So the issue with the bias is that the ordering, whether 1 is better than 2 or 2 is better than 1, will depend on how many samples I use to compute FID. It should be a... Yep. But you know what? So let's say that I choose 10% of my data for FID, and then I find model 1 is best. But then if I use 20% of my data, I might find that model 2 is best. And it's not that, you know, it's not that model 1 is really better than model 2 or model 2 is really better than model 1. It's just that I've used different numbers of samples, and my bias term is sort of shifted around differently for each model. And so that sort of flips the ordering. So, if the ordering didn't care about how many samples I would use, then I could use FID. I would just say, like, I know there's a bias, I know it's not 0, but at least I know the ordering is right. At least I know model 1 is the winner, model 2 is second, model 3 is third. But the trouble is that ordering changes as I see more or fewer samples. And that's a much bigger problem. Because then, I would publish my paper with 10,000 samples, which makes my model win. Then next year, someone is going to publish a paper with 20,000 samples that makes their model win. Like, that's not interesting science. Yeah. So what we have done, and this is the measure that we use, is something called kernel inception distance. So what we use the same pull-3 layer of inception, but what we do is rather than computing the Frechet distance, so this, fitting a Gaussian and computing this FID on it, we just use a third-order polynomial kernel. So this is just like a very crude, very simple kernel that looks at the mean, the variance, and the third moment. So the advantage of this is that it's unbiased. So I'm computing here the KID between two halves of my CFAR dataset. And in this case, you can see that there is a variance, but the mean is 0. So at least I don't have a bias. The variance, of course, is dropping as I see more samples, but I don't have this bias problem. So the ordering of my algorithms shouldn't care about how much data I've seen. So, this is what we're using now. It's not the last word, okay? So, for instance, pull-3 layer of inception is a completely arbitrary choice. Like, these are image features, maybe there are better image features. There's also a subtlety. So imagine that my generator just decided to memorize my training data. So all it does is it literally saves all of the training data to a hard drive. And then when I ask it to generate a point, it retrieves a point from my hard drive and just displays it. This is not a very useful generator. It's a memorizer. It's like studying for an exam by just memorizing the textbook and like copying bits down in answer to every question. Okay, so this FID would be perfectly happy with a memorizing GAN, because it would look at the distribution of the images out from the memorizing GAN, it would compare it to the reference samples, and it would say, yeah, these are fantastic samples. They look just like CFAR, which they do because I copied them. So this doesn't detect that problem. It doesn't detect the memorization problem. There is some work, I think, by Sanjeev Arora, where he's trying to combat the memorization problem using this birthday paradox. So what he does, he runs his GAN, and it generates images, but if it's memorizing stuff, at some point it's going to generate the same image twice, because it's just retrieving images from the hard drive, and it's just going to copy the same image again. If you ask it for enough images, at some point it's going to get an image 2 times. This is actually a pretty smart way of getting around this memorization. The issue is that like a GAN doesn't generate exactly the same image twice. It might generate, well, somewhat close images. So the way that he did this in practice was to run an Amazon Mechanical Turk experiment, and the Mechanical Turks would detect matching images. So that is very expensive. You can't really do it routinely. But this is at least an idea. Yep. Yeah. So in fact, looking for matches using nearest neighbors, like that's a reasonable thing. So the images that were presented to the Mechanical Turkers were sort of extracted using some crude nearest neighbor thing. I mean, it's a little bit tricky because of the way that GANs generate images. It's, you may not get exact matches, and so, it's not something you can just run and hope that it works, but at least it simplifies the problem so that the Turks aren't wasting time. Yeah. Yep. Right, so yeah, the one that takes into account the classes is the original inception distance. I think though, this relying on a classifier I think really restricts the class of problems you can use with GANs, because for many GANs it's not that you want to generate like pictures of everything in the world, which a classifier can apply on. Like usually in a GAN, your task is really to generate just one class of objects, like bedrooms or so. Or, you know, with things in image, like image inpainting, like, you know, it's not that you're trying to sort of, generate everything. It's that you're trying to accomplish a very narrow task, and so you can't use a classifier really as a benchmark. Yes, okay. So, oh yeah, hello? Yep. Then you better not use inception features. So inception features are really, because for our paper we were dealing with stuff for which they're good. If I'm doing like audio, you know, evidently not, right? You would want to use something for audio classification. So like the sort of choice of features for your GAN benchmarking is an art form. It's not something where there's a sort of rigorous theoretical guideline to choosing one or the other set. You should just find, you know, a good supervised learning algorithm for that problem. You should find the features that that's using, and then you can use that in KID. You know, it's not that there is like a correct answer. It's just that there are some answers that are reasonable heuristics. Yep. Okay. It wouldn't be a GAN paper without pretty pictures, so we're going to do the pretty pictures now. When we did the NeurIPS paper last year, we compared against the iClear papers from earlier that year. You know, the field is moving very fast, so whenever you do a paper, you have to just compare with the papers that came out in the previous conference, which is what we did. Since then, of course, you know, iClear this year is even better again, so yeah, it's a sort of arms race which never ends. One paper that I really liked, and which I want to alert you to, is this spectral normalization. So this is a trick for training GANs that whatever your GAN, you should use. What it does is that it controls the spectral norm, so the largest eigenvalue, of the filter matrices for your critic. This turns out to be incredibly useful in making your critic stable when you're training. We use it, everyone uses it, you should use it. Okay? And we are comparing with, you know, our method using, you know, both this trick and the problem-specific gradient regularizer with this earlier paper. We also compare with our own earlier paper, which is basically like, you know, a variant of the Wasserstein GAN. And then we compare also with this boundary-seeking GAN from Yoshua Bengio's group. So obviously celebrity faces are very important. These days, of course, you know, bear in mind we used a very crude DC GAN generator for this. So, you know, if you use a smarter generator network, you're going to get much, much better pictures. Our purpose in these experiments was not to get the best pictures, it was to say, like, given a generator network, how well could you train it? So even a simple generator network is enough to answer that question, because, you know, the common factor across all these experiments is that the generator network is fixed, and I'm changing my critic. I'm hopefully improving my critic. So in this case, you know, given, you know, we had limited computational resources, we're not NVIDIA, so given this rather simple generator network, and using our, you know, our data-specific critic class, or our problem-specific critic class, we were able to do better. We also have a really funny picture here, so yeah. The other thing we did, which at least at the time when we published was a relatively new thing to try, is unconditional ImageNet. So ImageNet is obviously like a massive data set of millions of images in tons and tons and tons of different classes. Most people, when they train GANs on ImageNet, they restrict themselves to one class. Like they say, I'm going to generate dogs, or I'm going to generate, you know, aeroplanes. What we wanted to do is train a GAN on unconditional ImageNet. So we're not conditioning on a class, we're just saying, like, draw me a picture of something that appears in the world. And in this case, you know, we competed with the two methods that were able to do that, which is the boundary-seeking GAN and the spectral GAN. And at least in FID score, but also in, you know, KID score and so on, we were able to do better. So, you know, this is at least promising. This tells us that we're on the right track, that using, you know, well, problem-specific critics allows us to improve our performance a bit. Okay, and I've got some more pictures, but yeah. So I should say that this gradient regularized MMD, which is down here, we have the code up, so you can actually play with it yourself and convince yourselves that it's good. You could also use it to generate portraits and sell those for a lot of money in auction houses in the UK, so I encourage you to do that. So how are we for time? Okay, so we have, let's say, 15 minutes. What I'm going to do is, in the last minutes, is to switch slide decks and go for this one. Okay, so slight change of problem setting. I've actually, before I do my change of problem setting, first of all, are there any final questions about the GAN stuff? Where? Over here. Okay. Yeah. Sorry, could you repeat that? That's right. Yep, no, that's a very good question. I'm going to go back to the slide deck so I can repeat your question with reference to an equation. Oops, no, I don't want that. I want this. Let's, oops, wrong clicker. Right. So here was the question, right? I've got, here I've got, let's go to this version, 3 terms. And, indeed I've got a sum of 2 terms plus a lambda times the third term. And the question was, well, if I set my lambda really large, then the third term dominates and solves everything or controls everything. If I set my lambda too small, that third term drops out. So absolutely, that is correct. You need to set it carefully. And again, like there is no sort of theory guiding us in setting this. What we found in practice was in the early stages of the optimization, it was important for these first 2 terms to dominate. So we had lambda small. In the later stages of the optimization, it was important for the last term to dominate. So as we optimized, we would sort of like inch up our lambda a little bit. It makes sense in the sense that like these first 2 terms sort of determine the structure of our kernels in the early stage of the optimization, and we want to sort of, control the smoothness of our witness function, in a data-dependent way. This final term here is just a standard RKHS norm, so that's telling me that when I'm close to my solution, I should just use a smooth function of my critic features, which are now, learned reasonably well. Yep. But, this is absolutely an art form. Like there is no, when you look at the papers also, there's other things as well. So there's things like the learning rate. We figured out an automatic way to set the learning rate. We were looking at the KID score. If the KID score stopped improving, we'd drop our learning rate. So at least we're not setting our learning rate by like graduate student iteration. We're doing it now by something slightly more principled. But there is still some amount of like human intervention required to train these things. Yep. Yep. Yeah, so no, this is a very good point. So the point was that like there is apparently some amount of redundancy here because here I'm controlling in the final term the function smoothness. These terms also seem to control the smoothness. Controlling the spectral norm controls the smoothness because like lowering the spectral norm means I'm getting a smoother set of filters. This is true. One should be a little careful though. Remember that this final term is a a data-independent smoothness constraint. These first two terms are data dependent. So these terms are basically modifying my function class according to my problem. If rather than using P here, I use mu, like mu being the Lebesgue measure, like the flat measure, this would actually be a Sobolev norm. And I would recover just a kernel, actually. I could compute it in closed form. I wouldn't have to optimize. This P here is essential. The fact that I'm smoothing my function class using the target distribution, that actually pushes me away from a generic smoothness into a problem-specific smoothness. And so this, I think, is why, particularly in the early stages of the optimization, it's so essential to have this problem-specific regularizer, so that my function is sort of smooth across the support of my target, but is otherwise allowed to be steep and allow me to climb to my target. So term 3 is not doing the same thing as terms 1 and 2. Terms 1 and 2 are data-dependent smoothness. Term 3 is a data-independent smoothness. In the late stages of the optimization, this one can be handy. In the early stages, you really need these two. If you don't use these two, you're going to get this super sharp critic, which is your unhelpful critic. Yeah. For the spectral regularizer, it's also interesting to think, like what you can do as an ablation study. So you can turn on the spectral one and switch off the gradient one. You can turn on the gradient one, switch off the spectral one. And when you switch off one or the other, it still works. It just works less well. So it seems that the spectral norm regularizer and the gradient regularizer are doing slightly different things. And when you use both in combination, it's getting you better performance. Yeah. Yep. Yeah, so I mean, in the process of computing these, you can check that your gradient's not super spiky. And if your gradient blows up, you know that you're doing something wrong. Yeah, so that's, I mean, what helps the way that we check for bugs, so to speak, or misconvergences, is we compute every few iterations this KID score, this KID score. And if the KID score is sort of going down, then we know we're learning at a good rate. If it stops going down, we drop our learning rate. If it suddenly blows up, we know that we've, one of our filters has collapsed and is now rank 1 and you're just getting junk. So KID score is a very nice way of monitoring your GAN training. Any other questions? Okay, so let's just very quickly look at I wanted to just cover very briefly the problem of testing dependence, because I like this setting. For sure, we're not going to get through all the slides in 10 minutes, but I'm just going to give you like a little flavor of the problem of dependence testing, and then you can explore a bit for yourselves later, this area. Okay, so what is dependence testing? So dependence testing, like let's say I have, X and Y. So X is a picture, Y is a block of text. In this case, the block of text and the image are related. So if you know anything about dogs, if you read this text and then you look at the picture, you can see that actually the text and the picture are, they're dependent on each other. So the text describes the picture. What I want is now to discover automatically, without becoming an expert on dogs, whether there exists a relation between X and Y. So whether X and Y are correlated. So, as Joris will emphasize very strongly, correlation is not the same as causation. All I want to know is whether there exists a statistical dependence between X and Y, between my picture and my caption. Okay, so this is a very useful problem, I think, in a lot of data science. If you're doing neuroscience, maybe you have a stimulus and brain activity, you want to know if that stimulus and the brain activity are dependent or not, right? Does the stimulus and the brain activity have some covariation? Or, if you're increasing the price of an item and you've got a number of sales, is the number of sales and the price correlated or not? Okay, so very quick answer to that question. What if we used MMD? Fine, okay. So we could use MMD. And what we would do is we would use MMD between the joint and product of marginals. Because if there exists no dependence between X and Y, then the joint distribution is equal to the product of the marginals. Okay, stats 101. So we could compute that. Bad news is, I've just got a sample of X and Y together. I don't have a sample of the product of the marginals. But good news is I can easily simulate it. So imagine that I've got my pictures of my dogs and my little captions. Imagine I assign a random caption to each picture. I take my captions, I just scramble them round. If I assign a random caption to each picture, then maybe my dog gets this cat description, for example. So this is a way that I can simulate from the case where there is no dependence between x and y. I just take a random y and I assign it to each x. So that problem we can solve. This problem here, like what is the kernel that we use? That's a slightly harder problem. So let's say that I've got images and captions. I want a kernel on an image caption pair, right? I want a kernel that says if I have this image and caption, dog and description of dog, and I compare it to a second image and caption, cat description and cat, is the image caption pair of object 1 similar to the image caption pair of object 2? So a kernel over strings and images seems a very difficult thing to design because it has to take into account string features and image features. So, what's an option? Well, let's say that I have a really good image kernel, like a really good kernel on cats and dogs, and I have a really good kernel on text, okay, like a substring kernel. One way of getting a kernel on image caption pairs is just to take the product. Okay, remember the product kernel is a valid kernel. And from the lecture on Wednesday, like the product kernel is like an AND operation. So if the images are similar and the captions are similar, then the kernel is large. If either is small, then the kernel is small. Let's say that I use that, okay? So if I use that, then the MMD, or the squared MMD, is the trace of the matrix product of K, which is the kernel between my pictures, and L, which is the kernel between my captions. So let's say I have 10 pictures, right? I compute the kernel between every pair of pictures, I take the kernel between every pair of captions, and then I take the matrix product of these two. So let's look at this in images, right? Here is my K. So my K is my kernel between images. Okay, so I've got here like 2 dogs, so it has a large kernel value. These are a little similar. And then I've got like dogs and cats. So obviously like a dog and a cat is very different. Here I've got my kernel on text, okay? So the dog text is very similar to other dog text, but it's not very similar to cat text. So now I've got 2 matrices of similarities. I've got a matrix of similarities, a matrix of kernels, between every pair of animals, or animal pictures, and I've got a matrix of similarity between every pair of captions. Now let's say that the text and the images are dependent, okay? That means if I have similar pictures, I will also have similar captions, right? If I have got 2 pictures of a dog, then the captions will both refer to dogs. If I have dissimilar images, I will have dissimilar captions. If my picture is of a dog and of a cat, these are very dissimilar, my captions will also be dissimilar. It's like, dogs and cats. Okay? So I've now got these 2 matrices, and you can see that they have similar structure, like similar objects in view 1 are similar in view 2. Different objects in view 1 are different in view 2. So if these matrices look similar, then it's very likely that my images and my captions are dependent. If the matrices look completely different, then it would be very unlikely that the images and captions are dependent. Are there questions about that? Okay, so let's say that I have 2 matrices. I want to know if they look similar or not. Well, I could take the matrix dot product. If they're similar, the matrix dot product is large. If they're different, the matrix dot product is small. And that's exactly what I've done here. I've taken the matrix dot product of my K, my similarities between pairs of images, and my L, my matrix of similarities between captions. When that's large, it's very likely that the images and the captions depend on each other. When that's small, it's very unlikely. The captions are probably just random text. Okay, so this is what I do when I get the MMD when I'm using this product kernel. So, this is fine. It's actually pretty intuitive. There's a couple of questions though, right? So question 1, why the product kernel? Like that seems, I've just sort of like said that's a kernel, I could use it, why not? But it's completely arbitrary. Sums of kernels are also kernels. Or I could do something even more sophisticated. Like, why is the product kernel such a good idea? The other issue, I think, with this dependence measure is that it's not very interpretable. So, if I'm a biologist and I come to a machine learner and I ask them, is my brain signal dependent on my image data? And I, as a machine learner, tell them, yes, it is, because like this trace of matrix products is really large. That doesn't really tell me much about the nature of the dependence between the stimulus and the brain activity. It just tells me that there is a dependence. So I want something actually that's interpretable. I want something that I can actually like write in a paper like these are dependent because of this reason. All right. So do I have enough time for this? Okay, I have 2 minutes. That's enough time. Okay. So if I want to find like a complete, shall we say, measure of dependence, one needs to think about all the ways in which variables can be dependent. So here's a simple 2D example. X and Y here are dependent, right? They're linearly dependent. The Pearson correlation is very large. It's extremely significant. This is what, if you're taking undergraduate statistics and you're asked to find dependence, this is what you would do. And this is the kind of dependence you could find. What about this case? Are X and Y dependent? I mean, they are, because when X takes the value of 0.6, the variance of Y is very small. When X takes the value of 0.2, the variance of Y is very large. So clearly, the value of X and the value of Y have some dependence, but it's not linear. The Pearson correlation is not significant. It's very close to 0. What about this case? Okay, so here, the Pearson correlation is exactly 0, but X and Y are clearly dependent, right? When X is 0, Y can take either -1 or 1. When X is -1, Y takes the value 0. They're clearly dependent, but they're not correlated. I want a dependence measure that can find all of these measures of dependence. So what would I do? Let's look at this last case. Let's say I've got my X and Y, they have this ring dependence. What if I found a smooth mapping of X? I mapped X through this smooth function, and I mapped Y through this smooth function, okay? So I transform X and Y independently, each through its own smooth function. Suddenly my correlation is actually really high. So this is an interpretable notion of dependence. Dependence means I can find smooth transformations of my data that have a high correlation. And then I can tell my neuroscientist something. I can say like, look, if I map my data through this transform, and I map my, I map my stimulus through this transform, I map my brain activity through that transform, then I can find a high linear correlation. And these transforms are very simple transforms. It's not that I'm moving my data around the space arbitrarily. I'm finding very simple, very interpretable transforms of my data, which cause them to be highly correlated. And so this is a notion of dependence, I think, which is very natural. Are there questions about that? Yep. Right, yeah, so basically, when I say correlation, I mean I fit a straight line through my data, I look at the slope and I measure whether that slope is significantly different to 0. So obviously, if I fit a straight line through a ring, I get a flat line. If I fit a straight line through this sort of half moon, I get a line with a very large slope, and that slope is very significantly different to 0. So, this is an interpretable measure of dependence between variables. My question would be, what on earth does that have to do with this? And because we've got a short amount of time, I'm going to skip to the punchline. Here we go. So let's say, I've got my 2 smooth functions that transform my data to give a high linear correlation. I can find 2 smooth functions orthogonal to those first 2, which transform my data to have slightly lower but still significant correlation. And I can continue that. I can find functions orthogonal to the first 3, which give correlation that is, still significant but even lower again, and so on and so on. If I add the squared correlations together, I get the trace of the matrix product. So this is the link between the nice interpretable figures that I drew and this trace of dot product between K and L. So in a sense, like the trace of the matrix product is saying like, find me every pair of smooth functions for which I can get significant correlation and add the squares of these correlations. It's actually adding the squares of the covariances, not correlations, but because we've got -1 minutes, I'll just, leave it at that. So are there questions about this? Because I did do that rather fast. Yep. Right. I mean, so this, I was sort of giving, in a sense, like somewhat of an intuition as to why, if you see a scatter plot like this, you know, if I as a user see the scatter plot, I should conclude, even without testing, that there is a dependence between x and y. Because like knowing where x is tells you something about where y is. So for instance, knowing that x is 0 tells me that y is either -1 or 1. Knowing that x is -1 tells me that y is 0. Now imagine that I had perfectly uniform x and y. So the scatter plot would look like a square. Then knowing where x is doesn't tell you anything about where y is. Wherever I choose x, y is going to have the same uniform distribution. Or in other words, pxy is equal to px times py. So that's just a sort of like, you know, a sort of a piece of advice for like, you know, data scientists. If you glance at these scatter plots, you can often see that there's dependence even before you do a test. Okay, so I think I probably better stop now, so I'm going to go to my final slide, which is here with the cuddle bear. So, thank you.